Look up at the night sky, and you'll see countless stars, pinpricks of light in an endless sea of darkness. But hidden among them are cosmic enigmas that defy explanation, places where the universe seems to bend its own rules. One of the most baffling of these is Centaurus A galaxy so strange, so utterly unlike anything else in the cosmos, that astronomers have spent decades trying to unravel its secrets. Picture a colossal, warped disk of stars and dust, twisted by forces we barely understand, with a monstrous black hole at its heart spewing jets of energy that stretch halfway across the universe. This isn't just another galaxy, it's a cosmic puzzle box, packed with 30 bizarre phenomena that challenge everything we thought we knew about how galaxies behave. What makes Centaurus so special? For starters, it's a cosmic chimera, a bizarre hybrid of galaxy types with features that shouldn't exist together. Most galaxies fall into neat categories, elegant spirals like our Milky Way or smooth, featureless ellipticals, but Centaurus A, it's a chaotic mashup of both, as if the universe couldn't decide what to make of it. Then there's the dark, jagged dust lane slicing across its center like a scar, a remnant of some ancient collision that left it forever changed, and that's just the beginning. Lurking within its core is a supermassive black hole with an appetite so voracious. It blasts out jets of plasma at nearly light speed, jets so powerful they can be seen with radio telescopes from millions of light years away. But the strangeness doesn't stop there. Centaurus A is a treasure trove of cosmic oddities, from mysterious streams of stars torn from smaller galaxies to ghostly radio lobes that span distances larger than the galaxy itself. Some of its phenomena are so extreme they shouldn't be possible under the known laws of physics. Others hint at events so cataclysmic they rewrite the history of the universe. And that's why we're diving into all 30 of these wonders today, because each one holds a clue, a piece of the puzzle that could help us finally understand this galactic enigma. So buckle up. We're about to take a journey into one of the most mysterious corners of the cosmos, where every discovery raises new questions and the universe keeps its deepest secrets hidden in plain sight. At the heart of Centaurus lies one of the most violent objects in the universe, a supermassive black hole with behavior so unpredictable, it throws textbook astrophysics into question. While most black holes quietly consume matter in a slow, steady spiral, this one erupts like a cosmic dragon, shooting colossal jets of superheated plasma at nearly the speed of light. These jets aren't just powerful, they're erratic, flickering on and off in ways that defy our understanding of how black holes feed. Imagine a fire hose blasting water in random directions, twisting and bending without warning, and you'll get a glimpse of the chaos unfolding here. What makes this black hole so unusual? For one, its sheer size, clocking in at around 55 million times the mass of our Sun. It dwarfs Sagittarius, a star, the black hole at the center of our Milky Way, which weighs in at a relatively modest 4 million solar masses. But mass alone doesn't explain its bizarre activity. Unlike Sagittarius, a star which feeds on a thin, steady stream of gas, Centaurus A's black hole seems to gulp down matter in fits and starts, as if it's feasting on an unstable cosmic buffet. Then there's the mystery of its jets. Normally, black hole jets shoot out in relatively straight lines constrained by magnetic fields, but Centaurus A's jets wobble violently, bending at sharp angles before stretching over 1 million light-years into space. Some scientists think these contortions come from a past collision, a galactic crash that left the black hole's feeding disk tilted and unstable. Others speculate there's something fundamentally different about the way this black hole interacts with its surroundings, a hidden variable we haven't discovered yet. One thing's certain, this isn't just a louder, angrier version of the black holes we're used to. It's behaving in ways that challenge our models. If black holes were engines, most would hum along predictably. But Centaurus A's engine sputters, coughs, and occasionally roars to life in outbursts that light up the sky across multiple wavelengths. Every flicker, every bend in those jets is a clue, a piece of a puzzle that could rewrite what we know about these cosmic monsters. And that's just the first of 30 mysteries this galaxy holds. Slashing across the face of Centaurus like a jagged cosmic scar lies one of its most striking features, a dark, twisted dust lane that defies simple explanation. This isn't just a simple band of debris, it's a warped, chaotic structure that twists and contorts through the galaxy's heart, as if some unseen hand crumpled it like paper. Most galaxies with dust lanes display orderly, symmetrical patterns, but Centaurus A's looks like it survived a cosmic car crash, and that might not be far from the truth. The leading theory suggests this bizarre feature is the aftermath of a colossal galactic collision billions of years ago. Picture two galaxies, one a massive elliptical, the other a smaller spiral plunging into one another in a slow-motion disaster. As they merged, the spiral's delicate disk of gas and dust would have been shredded, its structure torn apart by tidal forces. But instead of scattering evenly, some of this material may have settled into the lopsided, winding lane we see today, forever frozen in the aftermath of that ancient violence. Yet there's a twist. Some researchers argue the dust lane's extreme warping can't be explained by a single collision. Computer simulations show it might require multiple galactic encounters, each gravitational encounter bending the lane further, like taffy being pulled in different directions over cosmic time. Others propose the supermassive black hole's intense gravity plays a role, its pull distorting the dust like a funhouse mirror. There's even a fringe hypothesis suggesting the lane isn't debris at all, but a rivers of cold gas being funneled into the black hole, a cosmic conveyor belt we're seeing edge on. What makes this mystery so compelling is how much it reveals about galactic evolution. Normally, when galaxies merge, their dust eventually settles into predictable patterns or gets blown away entirely. Centaurus A's dust lane is a stubborn outlier, preserving clues about the chaos of its past. By studying its twists, astronomers can trace the history of not just one collision, but potentially an entire series of violent events that shaped this galactic oddball. And with every new observation, the story gets stranger. Recent infrared data shows pockets of star formation hidden within the dust, suggesting it's not just a relic but an active, evolving structure. This isn't just a fossil of destruction, it's a living puzzle, one that challenges our ideas about how galaxies grow and change. If we can unravel the secrets of this warped lane, we might unlock truths about how the universe builds and rebuilds its most massive structures. And as we'll see, it's just one of many features in Centaurus that refuse to play by the rules. Stretching far beyond the visible boundaries of Centaurus A, twin colossal structures loom like ghostly echoes of past violence, the galaxy's enormous radio lobes. These vast ballooning regions, each spanning over 1 million light-years, glow not with starlight but with powerful radio waves, signatures of electrons spiraling at nearly light speed through magnetic fields. What's astonishing isn't just their size but their eerie symmetry. In a universe where chaos reigns, these lobes mirror each other with near-perfect precision, as if carved by an invisible cosmic hand. The energy required to create these structures is almost unimaginable. The lobes are fueled by the galaxy's supermassive black hole, which channels matter and energy into those high-speed jets we saw earlier. But here's the puzzle. When those jets slam into the intergalactic medium, they should distort, warp, or even collapse unevenly as they encounter pockets of denser gas. Instead, Centaurus A's lobes remain strikingly balanced, their smooth curves defying expectations. It's like watching two soap bubbles inflate in perfect unison despite being poked by random needles. Scientists have proposed several theories to explain this symmetry. One suggests the surrounding environment is unexpectedly uniform, a cosmic, empty hallway that lets the lobes expand evenly. Another posits that magnetic fields, woven through the lobes like invisible scaffolding, stabilize their structure against disruptions. But the most tantalizing idea involves the black hole's feeding cycle. Some researchers think the jets aren't continuous but pulse in synchronized bursts, like a pair of cosmic bellows pumping energy outward in rhythmic waves. Each pulse would reinforce the lobe symmetry, smoothing out any irregularities over millions of years. Then there's the mystery of their longevity. These lobes aren't a fleeting phenomenon. They've persisted for tens of millions of years, far longer than typical jet-driven structures. Normally, such features fade as their energy disperses, but Centaurus A's lobes seem almost frozen in time. Observations reveal faint, older layers nested within them, like rings in a tree trunk, hinting at multiple eruptions from the black hole. Each layer adds to the enigma, suggesting this galaxy has been quietly perfecting the art of balance across epochs. What makes these lobes truly extraordinary is what they represent, a fossil record of the black hole's activity. By studying their shape and radiation, astronomers can piece together a timeline of outbursts, quiet periods, and even changes in the jet's direction. They're not just static relics, they're dynamic archives, encoding secrets about how supermassive black holes influence their surroundings over cosmic timescales. And in Centaurus A's case, they're whispering a story we're only beginning to understand. Gamma-ray bursts are some of the most violent explosions in the universe, flashes of light so intense they can outshine entire galaxies in seconds. Normally, we associate them with distant cosmic catastrophes like colliding neutron stars or dying hypergiant stars, but Centaurus A throws a curveball. It produces gamma-ray bursts too, and they don't behave like anything else we've seen. These aren't one-off explosions from deep space. They're erratic, high-energy flashes coming from the galaxy itself, and no one's entirely sure why. Most galaxies with supermassive black holes emit steady streams of high-energy radiation, a predictable byproduct of matter heating up as it falls toward the event horizon. Centaurus A's gamma emissions, though, are anything but steady. They arrive in unpredictable spikes, sometimes multiple bursts in a week, then silence for months. It's as if someone's flickering a cosmic flashlight on and off at random intervals, and the pattern defies every model astronomers have tried to fit to it. One leading theory points to the black hole's chaotic feeding habits. Unlike orderly systems where gas spirals in smoothly, Centaurus A's black hole might be swallowing clumps of matter in violent, irregular gulps. Picture a bonfire where someone occasionally tosses in a log. Each impact sends up a burst of sparks. In this case, those sparks could be powerful shock waves rippling through the infalling gas, accelerating particles to near light speeds and producing gamma rays. But there's a catch. Some bursts appear offset from the black hole itself, originating in the galaxy's outer regions where there's no obvious source of such extreme energy. This has led to wilder explanations like rogue neutron stars or dark matter interactions, ideas that push the boundaries of known physics. Even stranger, a few bursts seem to align with flares in the black hole's radio jets, suggesting some hidden connection between events light years apart. What makes these bursts so puzzling is their sheer inconsistency. If they followed a pattern tied to the black hole's rotation, for example, we might crack their code. Instead, they flare up like cosmic Morse code with no discernible message. Every time astronomers think they've pinned down a trigger, another burst breaks the rules. That's the real mystery here. Centaurus A isn't just breaking the mold. It's rewriting the playbook on how galaxies can produce high-energy radiation. And with each erratic burst, it reminds us that the universe still holds surprises we're only beginning to glimpse. Drifting silently through the darkness around Centaurus A, vast clouds of hydrogen gas stretch across hundreds of thousands of light-years, ghostly remnants of some ancient cosmic drama. These aren't the dense, star-forming nurseries we see in other galaxies. Instead, they're diffuse, almost ethereal structures, glowing faintly in radio wavelengths as if whispering secrets from the distant past. What makes them so puzzling isn't just their size, but their sheer abundance. Most galaxies have a sparse scattering of hydrogen in their outskirts, but Centaurus is wrapped in a sprawling, tangled web of it, far more than any current model predicts. The leading theory suggests these clouds are the cosmic fingerprints of a brutal galactic merger. When two galaxies collide, their gravitational tug of war can strip away vast amounts of gas, flinging it into the void like confetti. Over time, this material might settle into the eerie structures we see today, fossilized evidence of a violent encounter billions of years ago. But there's a problem with this explanation. Simulations show mergers typically leave behind more compact, clumpy debris, not the smooth, extended filaments surrounding Centaurus A. It's like comparing the aftermath of a car crash to a perfectly unraveled ball of yarn. Something doesn't add up. Another possibility involves the galaxy's monstrous jets. As those high-energy particles plow through intergalactic space, they could be heating and displacing hydrogen, pushing it into these vast, wispy formations. Imagine blowing on a dandelion. The seeds scatter in all directions, creating a delicate, floating structure. The jets might be doing something similar on a galactic scale, sculpting the gas into shapes we're only now beginning to map. Yet even this theory struggles to explain the cloud's sheer scale and their unexpected chemical composition. Some regions show traces of heavier elements, hinting they were once part of stars, not just primordial hydrogen. Then there's the mystery of their motion. These clouds aren't static, they're drifting at speeds that defy simple gravitational explanations. Some move in sync with the galaxy's rotation, while others streak in chaotic, unpredictable directions. It's as if unseen forces, perhaps dark matter or hidden magnetic fields, are tugging at them in ways we can't yet measure. What makes these ghostly clouds so revolutionary is the challenge they pose to our understanding of galaxy formation. If hydrogen is the universe's raw building material, then Centaurus A's excess suggests we've underestimated how much gas can linger in galactic halos. Some astronomers even speculate these clouds could be a hidden reservoir, slowly funneling material back into the galaxy to fuel future star formation. That would turn the entire life cycle of galaxies on its head. Rather than bleeding gas into space over time, Centaurus A might be hoarding it like a cosmic dragon sitting on a treasure of star-making fuel. Every new observation deepens the enigma. Recent studies reveal faint tendrils connecting the clouds to the galaxy's dusty core, like invisible umbilical cords feeding gas back into the system. Others show strange alignments with the radio jets, suggesting an intricate dance between the black hole's energy and the gas it's sculpting. Whatever the truth, one thing is clear: these ghostly clouds aren't just debris. They're a dynamic, evolving puzzle, one that could rewrite the rules of how galaxies grow, collide, and recycle their material across cosmic time. Deep within the swirling chaos of Centaurus A's core, a network of shadowy tendrils clings to the galaxy's heart like veins of cosmic soot. These aren't ordinary dust clouds, they're bizarre, thread-like structures astronomers call dark filaments, and they've resisted explanation for decades. Unlike the smooth dust lanes we see in other galaxies, these filaments are jagged, fragmented, and eerily precise, as if sketched by some unseen cosmic hand. Even with the sharpest telescopes, their true nature remains elusive, blurring the line between what we know and what we can't yet comprehend. At first glance, they resemble ordinary molecular clouds, cold, dense regions where stars are born. But here's the twist: these filaments don't behave like stellar nurseries. They're eerily silent, showing none of the telltale heat signatures or young stars we'd expect. Instead, they loom like frozen specters, absorbing light rather than reflecting it, their edges razor-sharp against the galaxy's glow. Some stretch for hundreds of light years, far longer than any known gas structure should survive without collapsing under its own gravity. It's like finding a bridge made of smoke that somehow stands firm in a hurricane. Theories abound, but none fully crack the puzzle. One camp argues these filaments are magnetic in nature, vast cords of charged particles woven into shape by the black hole's monstrous magnetic field. Imagine iron filings aligning around a magnet, but on a scale so vast it defies intuition. Others propose their shockwaves frozen in time, relics of past outbursts from the black hole that sculpted the gas into these ghostly ribbons. There's even a radical idea suggesting they're not gas at all, but swarms of rogue asteroids or comet-like bodies, though how such a swarm could remain stable is anyone's guess. The real enigma lies in their persistence. In most galaxies, structures like these should dissipate within millions of years, torn apart by turbulence or radiation. Yet Centaurus A's filaments endure, their shapes unnervingly intact. Recent observations add another layer of mystery. Some filaments glow faintly in X-rays, hinting they're threaded with ultra-high-energy particles. Could they be cosmic wires channeling energy from the black hole into the galaxy's depths? Or are they the scars of some ancient cataclysm, a collision so violent it left permanent marks on the fabric of the galaxy itself? What makes this phenomenon so compelling isn't just its defiance of explanation, it's the way it forces us to rethink the ordinary. If these filaments are something entirely new, something our current physics can't yet describe, then Centaurus A isn't just hiding secrets. It's rewriting the rules one shadowy thread at a time. Galaxies typically follow a simple rule when it comes to star formation. Gas clouds collapse under gravity, ignite new stars, and do so at a steady, predictable pace. But Centaurus A laughs in the face of this cosmic routine. Scattered across its twisted disk are pockets where star formation doesn't just deviate from the norm, it outright rebels. Some regions blaze with stellar births at rates that should be impossible, while others sit eerily dormant, as if someone flipped a switch to halt the process entirely. Take the galaxy's western filament, a tendril of dust and gas where telescopes have spotted newborn stars igniting at 10 times the expected rate. Normally, such frenzied activity requires vast reservoirs of cold, dense gas, the raw fuel for star formation. Yet here, the gas appears diffuse, almost wispy, lacking the concentration needed to explain the stellar fireworks. It's like watching a bonfire roar to life from a handful of damp twigs. Some astronomers speculate the secret lies in shockwaves from the black hole's jets, compressing gas clouds like an invisible hammer, triggering cascades of star birth. Others point to hidden strands of dark matter, their gravity silently herding gas into dense pockets we can't directly see. Then there's the opposite extreme, the so-called dead zones. These are vast swaths of Centaurus A brimming with gas that, by all rights, should be birthing stars by the thousands. Instead, they're eerily quiet. No stellar nurseries, no young blue stars, just a cosmic stillness that defies explanation. One leading theory blames the black hole's relentless energy output. Its radiation might be overheating the gas, preventing it from cooling and collapsing into stars. Imagine trying to light a candle in a hurricane. That's what star formation faces in these regions. But the real head-scratcher is how these extremes coexist. In most galaxies, star formation rates follow a smooth gradient, tapering off predictably from the core outward. Centaurus A, though, is a patchwork quilt of hyperactivity and silence with no clear pattern. Some suspect past mergers left the galaxy's GAS Chinese letter unevenly, like a splattered paint canvas. Others wonder if the black hole's jets are carving star-forming zones and dead zones like a cosmic sculptor, their energy alternately igniting and stifling stellar births as they sweep through the galaxy. What makes this phenomenon so tantalizing is what it reveals about the forces shaping galaxies. Normally, star formation is a local process governed by the cold, quiet collapse of gas. But in Centaurus A, it's clear something bigger is at work, a galaxy-wide tug of war between creation and destruction, orchestrated by the black hole's tantrums and the aftermath of ancient collisions. Every anomalous star cluster, every silent gas cloud is a clue, hinting at rules we're only beginning to decipher. And if we can unravel them here, we might finally understand why the universe builds stars so differently from one galaxy to the next. Globular clusters are the ancient sentinels of galaxies, dense, spherical collections of stars that formed billions of years ago, often before their host galaxies took shape. Most large galaxies, especially those like Centaurus A, are surrounded by hundreds, sometimes thousands of these stellar fossils. Yet when astronomers peer at Centaurus A, they find something bizarre, a glaring shortage. For its size and mass, this galaxy should have at least twice as many globular clusters as it does. It's like opening a treasure chest expecting gold, only to find half of it empty, without any obvious explanation for where the rest went. The mystery deepens when we compare Centaurus A to its galactic peers. Take Messier 87, another massive galaxy with a supermassive black hole at its core. It boasts a staggering 12,000 globular clusters, a glittering halo of stellar antiquity. Centaurus A, by contrast, has a meager few hundred. Even accounting for differences in environment and history, the deficit is too large to ignore. Where did they go? Did they never form in the first place, or were they violently stripped away? One leading theory points to the galaxy's turbulent past. If Centaurus A formed through a series of violent mergers, like the one that likely created its warped dust lane, the gravitational chaos could have torn apart countless clusters. Picture a demolition ball smashing through a chandelier. Only the sturdiest crystals survive. Some clusters may have been flung into intergalactic space, while others were swallowed whole by the galaxy's monstrous central black hole, their stars scattered like cosmic dust. But there's a flaw in this explanation. Mergers typically leave behind more globular clusters, not fewer, as the colliding galaxies contribute their own populations. This has led to a radical alternative. Perhaps Centaurus A never had many to begin with. Some researchers suggest its early environment was strangely devoid of the dense gas needed to form these clusters, leaving it perpetually starved of these stellar relics. Others propose a darker culprit. Ram pressure from the hot gas in its galactic neighborhood might have stripped away young clusters before they could fully form, like a cosmic tide washing away sandcastles. The most tantalizing clue comes from the clusters that do remain. Unlike the uniform, old populations seen in most galaxies, Centaurus A's globulars show a bizarre mix of ages and chemical compositions. Some are ancient, while others appear surprisingly young, as if the galaxy has been sporadically and inefficiently forming new clusters long after its peers stopped. This suggests something unique about its evolution, a stop-start rhythm of creation and destruction that left it with a fraction of the expected treasures. What makes this deficit so intriguing isn't just the missing clusters, it's what their absence reveals about the galaxy's hidden history. Globular clusters are cosmic time capsules, and their scarcity here hints at a past far more violent or far stranger than we've assumed. If we can unravel why Centaurus A lost them or never had them, we might unlock secrets about how galaxies grow, collide, and preserve their oldest stellar inhabitants. And in a universe where the rule is abundance, this outlier's emptiness speaks volumes. The supermassive black hole at the center of Centaurus A doesn't just spew energy, it sculpts it into one of the most peculiar structures in modern astronomy, an X-ray jet that doesn't travel straight but twists through space like a cosmic serpent. Unlike the ruler straight jets seen in most active galaxies, this one takes a sharp detour halfway through its journey, bending at an angle that should be impossible under normal circumstances. It's as if someone reached out and flicked a beam of high-energy particles mid-flight, sending it careening off course without breaking it apart. What could possibly warp a jet moving at nearly light speed? The leading suspect is gravity, specifically the invisible pull of dark matter. Simulations suggest Centaurus A might sit within an unusually dense knot of dark matter, whose gravitational influence could act like an unseen hand, nudging the jet sideways as it plows through this hidden landscape. Picture a river abruptly changing direction because of bedrock beneath the surface, except here, the bedrock is something we can't see, only infer from its gravitational fingerprints. But gravity might not be the only force at play. Magnetic fields stronger than any on Earth could also be shaping the jet's path. Some researchers propose that the black hole's rotation generates a colossal magnetic funnel, twisting the jet like a corkscrew as it exits. Others suggest the jet is plowing through pre-existing magnetic fields in the galaxy, which act like cosmic guardrails, forcing it into this bizarre detour. The strangest part, the bend happens remarkably far from the black hole, about 13,000 light-years out, which implies whatever's warping it has influence across staggering distances. Then there's the wildcard theory. The jet might be recoiling from the black hole itself. If the black hole was given a kick during its formation, perhaps from asymmetric gravitational waves during a merger, it could be moving through space while the jet continues in its original direction, creating the illusion of a bend. It's like a fire hose swinging while water continues straight, except on a scale where the hose is millions of times more massive than our Sun. What makes this phenomenon so crucial is what it reveals about extreme physics. Normally, jets are thought to be unstoppable, plowing through anything in their path. The fact that Centaurus A's jet bends suggests there are forces in the universe, whether dark matter, magnetism, or something else entirely, that can wrestle even relativistic plasma into submission. Every flicker of X-rays from that twisted beam carries clues about the hidden architecture of galaxies, written in a language of high-energy particles we're only beginning to decode. The deeper mystery: this isn't the only bend in the jet. Faint X-ray echoes suggest there might be multiple kinks along its length, like a cosmic slinky frozen mid-bounce. If true, it would imply the forces shaping it aren't one-time events, but ongoing processes, a dynamic struggle between the jet's raw power and the galaxy's hidden influences. And that makes Centaurus A's crooked jet more than just a cosmic oddity. It's a high-energy laboratory, testing the limits of how black holes interact with their surroundings in ways we never imagined. Nestled within the chaotic swirl of Centaurus lies a structure so odd, it seems almost out of place, a glowing patch astronomers call the red rectangle. Unlike the galaxy's usual blues and whites, this nebula burns with a deep, rusty hue, as if someone painted a geometric smudge across the cosmos. But the color isn't the strangest part. Its shape defies the organic curves of typical nebulae, its edges unnervingly sharp, like a cosmic gemstone cut with precision. At first glance, the red rectangle resembles planetary nebulae, shells of gas blown off by dying stars. But there's a problem. Those usually form around solitary stars in their final throes, not in the frenzied core of a galaxy like Centaurus A. This nebula's light spectrum adds to the confusion. Instead of the clean emission lines expected from heated gas, its glow is murky, littered with unexplained molecular bands that hint at complex carbon-based compounds. It's as if the nebula is filled with cosmic soot, a substance more commonly found in the atmospheres of distant stars than floating freely in space. So how did this anomaly form? One compelling theory ties it to the galaxy's violent merger history. When two galaxies collide, their gas clouds smash together at unimaginable speeds, creating shockwaves that can forge bizarre chemical compounds. The red rectangle might be a fossil of such an event, a pocket of gas where ancient turbulence cooked up exotic molecules, now glowing faintly in the aftermath. But there's a twist. Recent observations suggest the nebula isn't just passively reflecting past chaos, it's active. Infrared telescopes have detected strange, nested rings within it, like ripples from a stone tossed into a pond. Some researchers argue these rings are evidence of periodic outbursts from a hidden star, perhaps a binary system where one star is methodically stripping material from its partner. Each theft could trigger a new wave of gas ejection, layering the nebula in concentric shells of red glowing debris, the most tantalizing possibility. The red rectangle might be a cosmic hybrid, a structure born from both merger debris and ongoing stellar drama. If true, it would be a rare snapshot of two galactic processes colliding literally and figuratively. One thing's certain, this isn't just a pretty splash of color. It's a puzzle box locked with secrets about how galaxies recycle their material into strange new forms. And in Centaurus A, even the rectangles refuse to follow the rules. Cosmic rays, those high-energy particles racing across the universe at nearly light speed, usually barrel through galaxies unimpeded, their paths bent only slightly by magnetic fields. But Centaurus A throws a wrench into this textbook scenario. Observations reveal something bizarre, an invisible barrier surrounding the galaxy, deflecting certain cosmic rays with eerie precision. It's as if the galaxy built a magnetic force field, selectively filtering what gets in and out, a phenomenon unseen anywhere else in the cosmos. The mystery lies in the data. When astronomers trace the paths of cosmic rays from distant sources, they find a peculiar dip in particle counts near Centaurus A's outer regions. Some rays curve around it entirely, as if repelled. This isn't just a case of weak deflection, it's a full-scale cosmic roadblock. Normally, galactic magnetic fields might scatter particles slightly, but Centaurus A's fields are doing something far stranger, acting like a sieve, catching some rays while letting others pass untouched. What could create such a selective shield? One leading theory points to the galaxy's turbulent history. The aftermath of its past collisions might have tangled magnetic fields into a dense, chaotic web, with regions of intense magnetism woven like layers of a labyrinth. Cosmic rays entering this maze could scatter unpredictably, some getting trapped in magnetic dead ends while others slip through gaps. Think of it like trying to walk through a forest where some trees are invisible. You'd bump into obstacles you couldn't see, changing direction without knowing why. But here's where it gets weirder. The barrier seems to affect only certain energies of cosmic rays. Lower energy particles navigate it relatively unscathed, while higher energy ones, the ones that should punch through most barriers, are the ones being blocked. This energy-dependent filtering defies conventional models, where stronger particles typically plow through magnetic fields effortlessly. Some researchers speculate the galaxy's supermassive black hole plays a role, its jets injecting extra turbulence into the magnetic environment, creating pockets of extreme resistance. Others wonder if dark matter is involved, its gravitational influence amplifying the magnetic fields in ways we don't yet understand. The implications are staggering. If Centaurus A's barrier is unique, it could mean the galaxy is a cosmic outlier, its magnetic fields forged by a perfect storm of collisions and black hole activity. But if similar barriers exist elsewhere and we've just missed them, it might hint at a whole new class of magnetic phenomena, one that rewrites how galaxies interact with the high-energy universe. Every cosmic ray that bends or vanishes near Centaurus carries a coded message about forces we can't yet see, and decoding them might reveal hidden laws of physics operating in plain sight. What makes this phenomenon so tantalizing isn't just the barrier itself, but what it says about the galaxy's hidden anatomy. Magnetic fields are notoriously difficult to map, often revealing themselves only through their effects on passing particles. Here, they're not just passive threads woven through space, they're active, dynamic filters, sculpting the very particles that traverse the cosmos. And in Centaurus A, they're doing it with a precision that leaves us questioning everything we thought we knew about magnetism's reach. Just when astronomers thought they'd mapped Centaurus A's erratic behavior, the galaxy throws another curveball, sudden, violent infrared flares erupting from its core without warning. Unlike the predictable flickers of most active galaxies, these bursts blaze to life in a matter of hours, then vanish just as quickly, leaving behind only a fading thermal echo. It's as if someone's flicking a cosmic lighter deep within the galaxy's heart, producing flames that burn intensely before being snuffed out by unseen forces. What makes these flares so baffling isn't just their unpredictability, it's their sheer intensity. Infrared light typically signals warm dust or cooler stars, but these outbursts are far too bright for ordinary processes. Some pulses outshine the galaxy's entire core, suggesting temperatures rocketing to thousands of degrees in localized bursts. The leading culprit, the supermassive black hole's chaotic feeding habits. Most black holes consume gas in a steady, albeit messy, dribble. Centaurus A's monster, however, seems to gulp down matter in erratic spasms. Each time a particularly dense clump of gas or a stray star gets too close, the black hole's tidal forces tear it apart, creating a short-lived, superheated debris disk that glows fiercely in infrared before vanishing into the void. But there's a twist. Some flares don't align with any visible influx of material. Telescopes have caught flares erupting when the black hole's immediate surroundings appear eerily quiet, as if the energy emerges from nowhere. This has led to wilder theories, like magnetic reconnection events, sudden snaps in the black hole's magnetic field lines that release vast amounts of trapped energy. Imagine a rubber band stretched to its limit, then suddenly breaking. The stored energy has to go somewhere, and in this case it explodes as infrared light. Others speculate these flares could be evidence of hidden objects, swarms of asteroids or rogue planets falling into the black hole, their destruction playing out in thermal fireworks too faint to see in other wavelengths. The real enigma lies in the timing. Unlike X-ray or radio flares, which sometimes follow rough patterns tied to the black hole's rotation or jet activity, these infrared bursts seem utterly random. Some occur in clusters with multiple flares in a week, followed by years of silence. Others arrive as isolated spikes, solitary and unexplained. This lack of rhythm makes them nearly impossible to predict, turning every observation into a game of cosmic roulette. Yet within that chaos might lie a crucial clue. Recent studies hint that these flares could be the missing link between the black hole's feeding cycles and its larger-scale outbursts. Each infrared spike might represent a small-scale version of the galaxy's more violent eruptions, a miniature blueprint of how energy propagates from the core into the jets and lobes beyond. If true, decoding these flares could help us understand why Centaurus A's black hole behaves so differently from others and what truly fuels its cosmic tantrums. What makes these flares so mesmerizing isn't just their mystery, it's what they represent. A hidden layer of activity playing out in wavelengths our eyes can't see. While visible light shows us the galaxy's structure and X-rays reveal its violence, infrared uncovers the quiet, simmering moments between eruptions. And in Centaurus A, even those quiet moments are anything but calm. Encircling the chaotic core of Centaurus are like a cosmic halo. An immense ring of scorching gas glows with the heat of millions of degrees, an enigmatic structure astronomers have dubbed the Ring of Fire. This isn't some gentle, flickering flame. It's a seething loop of superheated plasma spanning over 3,000 light-years, where temperatures reach extremes that would vaporize any known material instantly. What's bizarre isn't just its existence, it's the fact that such a perfect circular structure could form in a galaxy known for its violent asymmetry. Most galaxies with active black holes show messy, turbulent gas flows like water spiraling down a drain. Centaurus A's ring, however, is eerily symmetrical, its shape so precise it looks almost engineered. The leading theory traces its origin to a cataclysmic event, a smaller galaxy plunging straight through Centaurus A's core like a bullet. The gravitational shockwave from that collision could have sent gas rippling outward in a near-perfect circular wave, which then heated to extreme temperatures as it interacted with the black hole's energy. Picture tossing a stone into a pond, then cranking the water's temperature to stellar levels. That's the kind of violent poetry we're dealing with here. But there's a problem with this explanation. Simulations show such collisions usually produce lopsided or fragmented rings, not this unnerving symmetry. Some researchers argue the ring might instead be a fossil shockwave from an ancient outburst of the black hole, a titanic belch of energy that pushed surrounding gas into this glowing formation. Others suggest it's a standing wave held in place by the black hole's gravity and magnetic fields, a cosmic version of a vibrating guitar string frozen in time. The real mystery lies in the ring's longevity. Gas this hot should dissipate or cool within millions of years, yet here it sits, still blazing as if the triggering event happened yesterday. Recent X-ray observations reveal faint, layered structures within the ring, like concentric ripples, hinting at multiple waves of energy refreshing it over eons. It's almost as if the black hole is periodically puffing up this structure like a cosmic bellows, keeping it alive against all odds. What makes the Ring of Fire truly extraordinary isn't just its defiance of physics, it's the clues it holds about Centaurus A's past. If the collision theory holds, the ring's size and temperature could tell us exactly when that galactic crash occurred. If it's powered by the black hole's outbursts, its layers might encode a history of the monster's feeding frenzies. Either way, this isn't just a glowing curiosity. It's a cosmic timestamp, a searing signature of violence etched into the galaxy's very heart, and one more piece of the puzzle that makes Centaurus unlike anything else in the known universe. At the very edge of Centaurus A's supermassive black hole, where gravity should shred everything apart, astronomers have spotted something that shouldn't exist: clusters of young, vibrant stars glowing defiantly in the shadow of destruction. These stellar newborns are dancing perilously close to the event horizon, a region so hostile that even light struggles to escape. According to every known model of black hole physics, tidal forces here should rip gas clouds apart long before they can collapse into stars. Yet there they are, shining like cosmic fireflies in a hurricane. How can stars form in such an apocalyptic environment? One theory suggests the black hole's own fury might be the unlikely midwife. The same jets that blast plasma across the galaxy could also create pockets of shelter. As these high-speed jets plow through surrounding gas, they might carve out dense, pressurized bubbles where material can cool just enough to collapse into stars. Imagine standing behind a blast shield during an explosion. The shockwave curves around you, leaving a small, oddly calm space in its wake. That might be what's happening here, with the black hole's own violence creating temporary sanctuaries for star birth. But there's a catch. These stars aren't just surviving, they're thriving, burning hotter and brighter than expected. Some exhibit bizarre chemical compositions, rich in elements that typically form only under extreme conditions. This has led to a radical alternative idea. Perhaps these aren't ordinary stars at all, but the remnants of shredded gas giants or failed stars, reignited by the black hole's intense radiation. It's like tossing damp wood into a furnace. Instead of burning away, the outer layers vaporize, leaving behind a denser core that suddenly flares to life. The real puzzle lies in their orbits. These stars don't spiral inward as they should. Many are locked in stable, almost circular paths around the black hole, as if some invisible hand is balancing them on a knife's edge. Normally, such precision requires delicate gravitational choreography, the kind that takes billions of years to establish. Yet spectral analysis suggests these stars are mere infants in cosmic terms, some only a few million years old. This paradox forces us to rethink not just star formation, but the very nature of black hole environments. If stars can arise in the most chaotic, violent corners of the universe, then our understanding of their birth and survival might be far too narrow. Centaurus A's rebellious young stars are more than just outliers. They're proof that even in the darkest, most destructive places, the universe finds a way to create. One of the most perplexing enigmas surrounding Centaurus isn't something we can see, it's what we can't. According to all conventional models of galaxy formation, this colossal structure should be cocooned within an immense, invisible sphere of dark matter, a gravitational scaffold 5 times more massive than all its visible stars and gas combined. Yet the numbers don't add up. Measurements of the galaxy's outer reaches reveal a shocking deficit. Centaurus A's dark matter halo is barely half as dense as it should be, as if someone siphoned away the universe's most mysterious substance and left the galaxy strangely exposed. This isn't just a minor discrepancy, it's a direct challenge to our understanding of how galaxies assemble. Dark matter isn't some passive backdrop. It's the cosmic glue that holds galaxies together, its gravity shaping the distribution of stars and gas across billions of years. Without it, galaxies like ours would fly apart, their stars scattering like marbles on a trampoline. So why is Centaurus seemingly defying this universal rule? One explanation could lie in the galaxy's violent merger history. When galaxies collide, their dark matter halos can be stripped away like shadows torn apart in a storm. Simulations suggest that if Centaurus underwent multiple catastrophic mergers, especially with smaller, gas-rich galaxies, the repeated gravitational assaults might have shredded its original dark matter envelope, scattering it into the wider cosmic web. Think of it like peeling an onion. Each collision might have stripped away layers of dark matter, leaving behind a galaxy oddly light on its invisible underpinnings. But there's a catch. Even in the messiest mergers, dark matter is notoriously resilient. It doesn't interact with normal matter or even itself. It simply passes through everything like a ghost. So while mergers might rearrange a halo's structure, they shouldn't erase it entirely. This has led to a more radical idea. Perhaps Centaurus never had a substantial dark matter halo to begin with. Some theorists propose it formed in an unusual region of the early universe, a cosmic void where dark matter was oddly sparse, forcing the galaxy to build itself with far less scaffolding than its peers. The plot thickens when we look at the galaxy's outermost stars. Their motion suggests something unseen is still exerting gravitational pull, just not enough to match predictions. This has sparked a wilder hypothesis. Maybe Centaurus A's missing dark matter isn't missing at all, but hiding in plain sight, transformed into an exotic state we can't yet detect. Some models suggest dark matter particles might interact weakly with each other in ways that alter their distribution over time, clustering differently than standard theories predict. If true, Centaurus could be the first evidence of self-interacting dark matter, a revelation that would rewrite the rules of particle physics. What makes this mystery so pivotal is what it says about the universe's hidden architecture. Dark matter halos aren't just theoretical constructs, they're the foundation of modern cosmology, the scaffolding upon which everything we see is built. If Centaurus genuinely lacks the expected halo, it could mean our models are fundamentally flawed, or that dark matter behaves in ways we've never imagined. Every star, every wisp of gas at the galaxy's edge carries a gravitational fingerprint of this anomaly, and deciphering it might require us to rethink not just one galaxy's history, but the very fabric of the cosmos. The irony is delicious. In a galaxy filled with visible oddities, from twisted dust lanes to rogue star clusters, the most baffling quirk of all might be the absence of something we can't even see. And that's what makes Centaurus so extraordinary. It doesn't just challenge what we know, it challenges how we know it. Among the many oddities in Centaurus A, some of the most ghostly are the faint echoes of light that arrive long after their source has vanished, like cosmic messages delayed by time itself. These aren't ordinary reflections, they're photons that took detours through the galaxy's tangled dust lanes, bouncing off microscopic particles for hundreds or even thousands of years before finally reaching us. The result, glimpses of ancient explosions unfolding in slow motion, their light stretched across centuries like a cosmic tape recorder set to replay. The most dramatic example comes from an outburst traced back to the black hole around 50 years ago. When telescopes first detected the initial flare in the 1970s, it seemed like just another violent hiccup from the galaxy's core. But decades later, astronomers spotted something bizarre: concentric rings of X-ray and optical light expanding outward from the same spot, each ring marking where the original blast light had scattered off dust layers at different distances. It's as if the explosion fired a bullet of light into a labyrinth of mirrors, with each reflection arriving at Earth years apart, painting a fragmented portrait of the event. What makes these echoes so valuable is their ability to reveal hidden chapters of the galaxy's history. By analyzing the timing and intensity of each delayed flash, researchers can reconstruct not just the original explosion's power, but the structure of the dust clouds it traversed, clouds too faint to see directly. Some echoes even hint at entirely unrecorded cataclysms, outbursts that occurred before modern telescopes existed, their existence betrayed only by these belated photons finally completing their journey. The strangest echoes, though, are the ones that don't match any known event. Faint spectral glows have been detected with no clear origin, suggesting Centaurus A's black hole might have quieter, more frequent tantrums than we've realized, outbursts too subtle to notice in real time, but whose afterimages linger like cosmic whispers. If true, it would mean we've only been seeing the loudest chapters of this galaxy's story, while a hidden tapestry of smaller explosions plays out unnoticed. These delayed messages do more than just illuminate the past. They're proof that even in astronomy, where light is supposed to be the fastest, most reliable messenger, the universe finds ways to surprise us, bending time and space to keep its secrets just a little longer. Among the violent outbursts and high-energy phenomena in Centaurus A, there's one glaring silence: neutrinos, the ghostly particles that usually flood from active galaxies, are strangely absent here. While galaxies with supermassive black holes typically shower the cosmos with these nearly massless particles, Centaurus emits barely a whisper, as if someone muted the universe's most elusive messengers. This quiet baffles physicists because neutrinos are born in the most extreme environments where particles are accelerated to unimaginable energies. And if any galaxy should be screaming in neutrinos, it's this one. To grasp why this silence is so puzzling, consider how neutrinos usually behave. In most active galaxies, they're produced when protons, accelerated to near light speed by the black hole's jets, collide with other particles. These crashes spawn a cascade of secondary particles, including neutrinos, which then zip through space unimpeded, passing through planets and detectors alike like spectral bullets. The Ice Cube Neutrino Observatory in Antarctica, for example, routinely catches these particles from distant galaxies, their energies so high they're often dubbed cosmic cannonballs. Yet when scientists point their detectors toward Centaurus A, the expected torrent is more like a light drizzle. So where are the missing neutrinos? One possibility is that Centaurus A's black hole is an inefficient particle accelerator. While its jets are powerful, they might lack the right conditions, perhaps a specific magnetic field structure or particle density, to smash protons together at the rates needed to produce a strong neutrino signal. Imagine a car engine revving loudly but missing the spark plugs. It makes noise but doesn't convert fuel efficiently. That could explain the discrepancy. But there's a twist. Some theorists argue the neutrinos might be there, just not in the form we expect. If Centaurus A's jets are tangled or kinked, as observations suggest, the particles inside might be ricocheting in ways that spread out the neutrino emission, making it too diffuse for current detectors to spot against the background noise. It's like trying to hear a whisper in a crowded room. The signal gets lost in the static, Alternatively, the neutrinos could be arriving at lower energies than typical for active galaxies, slipping under the detection threshold of experiments like IceCube. The most tantalizing explanation, though, is that we're seeing a fundamental difference in how black holes channel energy. While most active galaxies convert a predictable fraction of their power into neutrinos, Centaurus A's black hole might be redirecting that energy elsewhere, perhaps into those bizarre X-ray jets or the mysterious infrared flares. If true, it would mean the galaxy isn't just an outlier in visible or radio light. It's breaking the rules on the subatomic level too. This silence isn't just a curiosity, it's a potential window into the unknown. Neutrinos are notoriously hard to detect, but they're also pristine messengers, unaltered by magnetic fields or dust. Their absence here might signal a new class of black hole behavior, one that challenges our understanding of particle acceleration in the most extreme environments. And if Centaurus A is hiding its neutrinos, what other secrets might it be keeping? Stretching far beyond the visible boundaries of Centaurus A, an eerie ultraviolet glow blankets vast regions of the galaxy like an otherworldly aurora. This isn't the familiar blue tint of young stars or the soft haze of scattered starlight. It's a diffuse, almost ghostly emission that defies simple explanation. What makes this UV halo so perplexing is its disconnect from the galaxy's known star-forming regions. Normally, ultraviolet light signals hot, newborn stars, but here it appears where no such stars exist, as if the galaxy is leaking invisible energy from its seams. The puzzle begins with the halo's distribution. Instead of clustering around areas rich in gas and dust where stars typically form, this UV glow sprawls across seemingly empty regions, even reaching into the galaxy's faint outer edges. It's like finding a city's streetlights shining brightest in the abandoned suburbs rather than downtown. Some researchers initially thought it might be starlight scattered by dust, but the spectrum tells a different story. The ultraviolet signature matches neither aged stars nor newborn ones, but something in between, or perhaps something entirely different. One leading hypothesis points to an unseen population of rogue stars flung from the galaxy's core during ancient collisions. These stellar nomads wandering the galactic outskirts could theoretically emit UV light as they age, but there's a catch. The halo's brightness far exceeds what such scattered stars should produce. Another theory suggests the glow comes from shock-heated gas, interstellar material superheated by the black hole's jets or by galactic collisions until it radiates in the ultraviolet. Yet detailed observations reveal the gas temperatures don't quite align with this explanation either. The most tantalizing possibility involves a process called fluorescence. Just as certain minerals glow under UV light on Earth, vast clouds of hydrogen in Centaurus A might be absorbing high-energy radiation from the black hole and re-emitting it at ultraviolet wavelengths. Imagine the galaxy's core as a black light and its outer gas as invisible ink suddenly illuminated. This would explain the diffuse, widespread nature of the glow, but it still leaves questions. For fluorescence to work, the gas should show very specific emission lines, and so far, the data only partially matches those expectations. What makes this phenomenon truly remarkable is how it challenges our assumptions about galactic energy budgets. If the UV halo isn't tied to star formation or simple scattering, then Centaurus A is somehow generating or recycling energy in ways we've never observed elsewhere. Every photon of this mysterious light carries clues about the galaxy's hidden workings, from the afterlife of ancient collisions to the subtle interplay between its black hole and the surrounding void. And until we unravel its secrets, this ghostly glow remains a silent testament to how much we still have to learn about the universe's most enigmatic structures. Scattered throughout Centaurus A, vast clouds of hydrogen gas drift like cosmic fog banks until they abruptly vanish. These aren't slow fades or predictable dissipations. One moment they're there, glowing faintly in radio telescopes, the next they're gone without a trace, leaving astronomers scrambling for explanations. This isn't just gas slowly dissipating into space, it's more like a magician's trick, where the disappearance happens faster than physics should allow. The leading suspect is the galaxy's supermassive black hole, lurking like a cosmic vacuum cleaner. When gas clouds wander too close, the black hole's gravity could shred them apart in a process called spaghettification, stretching the gas into thin streams that vanish past the event horizon. But here's the catch: some clouds disappear from regions surprisingly far from the black hole's immediate grasp, areas where tidal forces shouldn't be strong enough to explain the sudden evaporation. It's like watching puddles dry up on a cool day with no sunlight. Something else must be at work. That something else might be the black hole's furious energy output. The same jets that carve through the galaxy at near light speed could be generating powerful winds, invisible hurricanes of charged particles that scour gas clouds from the inside out. Picture a sandcastle hit by a fire hose. The structure doesn't just erode, it explodes into particles too fine to detect. These winds might explain why some clouds vanish almost overnight in cosmic terms, their atoms blasted into intergalactic space before telescopes can track their demise. Yet there's a third, even stranger possibility. The clouds might not be disappearing at all, but transforming. Intense radiation from the black hole could be ionizing the hydrogen, stripping away electrons until what was once a detectable gas cloud becomes an invisible plasma, undetectable at the wavelengths we typically observe. It's the cosmic equivalent of clear ice melting into transparent water. The material still exists, but our instruments can no longer see it. The real mystery lies in the timing. Some clouds persist for centuries, while others blink out in mere decades, with no obvious pattern to their longevity. Recent observations suggest a tantalizing clue: clouds near the galaxy's warped dust lane tend to vanish faster, hinting that the aftermath of ancient collisions might have left these regions more vulnerable to disruption. Other studies show that clouds with complex internal structures resist dispersion longer, like a knotted rope holding firm against the wind. What makes these vanishing acts so crucial isn't just the missing gas, it's what their disappearance reveals about the hidden forces shaping galaxies. Every evaporated cloud is a lost opportunity for star formation, a potential solar system that will never be. By studying how and why they vanish, we're glimpsing the delicate balance between creation and destruction in the cosmos, and in Centaurus A, that balance is tipping in ways we're only beginning to understand. One of the most peculiar symmetries in Centaurus isn't found in its light or structure. It's hidden in the invisible magnetic fields that weave through its colossal radio lobes. While most galaxies with jet-powered lobes show chaotic, tangled magnetic lines, here they align with eerie precision, mirroring each other across millions of light-years like cosmic Rorschach ink blots. This isn't just a happy accident, it's a clue that the galaxy's violent heart operates by rules we've yet to decipher. The mystery starts with how these fields form. Normally, magnetic fields in galactic lobes arise chaotically as jets slam into intergalactic gas, twisting and stretching like taffy in a child's hands. Yet in Centaurus A, the fields in the northern and southern lobes are near-perfect mirror images, their patterns so symmetrical they resemble the wings of a butterfly. This precision suggests an unseen order governing the black hole's outbursts, as if some hidden mechanism keeps its tantrums perfectly balanced. One theory points to the black hole's spin. If the monster rotates at a steady rate, its jets could act like a pair of synchronized cosmic fire hoses, spraying magnetized plasma in identical arcs. The resulting fields would then fossilize into these mirrored shapes as the lobes expand. But there's a flaw. Even the most stable black holes should show slight asymmetries, as minor fluctuations in gas supply or magnetic turbulence disrupt the flow. Centaurus A's lobes, however, maintain their symmetry across scales that defy these expectations. Another idea involves the galaxy's environment. some researchers propose that the intergalactic medium surrounding Centaurus A is unusually uniform, a cosmic still pond that lets the lobes expand without distortion. In most galaxies, dense gas clouds or nearby galaxy clusters would warp the lobes unevenly. Here, the lack of external interference might allow the magnetic fields to preserve their mirror-like perfection. But the most intriguing possibility is that we're seeing evidence of a feedback loop between the lobes and the black hole itself. As the jets pump energy outward, the expanding lobes could generate pressure waves that travel back inward, subtly tuning the black hole's next outburst to maintain symmetry. It's like a musician adjusting their playing based on the echo in a concert hall, except the music here is the hum of magnetized plasma, and the hall is a million light-year-wide cavity of space. What makes this phenomenon so revolutionary isn't just the symmetry itself, it's what it implies about how black holes and their surroundings communicate. If Centaurus A's fields are truly locked in this mirrored dance, it suggests a level of coordination between the galaxy's core and its farthest reaches that challenges our models of cosmic feedback. And in a universe where chaos usually reigns, this strange harmony might be the key to understanding why some galaxies, against all odds, manage to keep their balance. Deep within Centaurus A's spiral arms, astronomers keep catching glimpses of dying stars that don't play by the rules, stellar explosions that flare with all the brilliance of supernova, then disappear without a trace. These phantom explosions brighten suddenly over days or weeks, matching the classic signature of a star's catastrophic death, only to fade into nothingness without leaving behind the glowing nebula or dense stellar corpse that should mark a supernova's aftermath. It's as if the galaxy is staging cosmic fireworks displays with invisible pyrotechnics, taunting us with stellar deaths that vanish before we can study them. The first such event was dismissed as an observational fluke until more kept appearing. Unlike normal supernova, which leave behind either neutron stars or black holes encircled by expanding debris clouds, these fake-out explosions leave absolutely nothing behind. Telescopes pointed at their locations months later find only undisturbed starlight, as if the eruption never occurred. The leading explanation involves massive stars with unusual internal structures, perhaps behemoths so dense that when their cores collapse, the entire star implodes completely without the traditional explosive rebound that lights up a supernova. Imagine a building collapsing straight into its basement without any outward blast. The structure vanishes, but the neighborhood shows no damage, but there's a catch. Some of these events occur where no massive stars should exist. In regions of Centaurus are too young to host stars old enough to die. This has spawned wilder theories like rogue black holes or dark matter interactions triggering runaway fusion in otherwise stable stars. One particularly radical idea suggests we're seeing the death throes of stars from a parallel universe, hypothetical mirror matter objects whose physics allows complete annihilation without remnants. While speculative, it highlights how thoroughly these phantoms defy conventional astrophysics. What makes these events so vexing isn't just their disappearance, it's their inconsistent behavior. Some brighten and fade smoothly like dimmed lights, others flicker erratically before vanishing. A handful even reappear years later in the same spot, something no known stellar object should do. If these are indeed supernova, they're rewriting the textbook on how stars die. If they're something else entirely, Centaurus A might be hiding forms of stellar existence we've never imagined. Every time telescopes catch another one of these phantom flares, it's like receiving a cosmic riddle with no answer key. And in a galaxy already overflowing with mysteries, these vanishing acts might be the most tantalizing clues, yet hinting that even the deaths of stars can unfold in ways we're only beginning to glimpse. Tucked away in Centaurus A's chaotic outskirts lies a cosmic anomaly so extreme. It's been dubbed the particle storm, a localized region blasting out cosmic rays with energies that dwarf anything our most powerful particle accelerators can produce. These aren't your average high-energy particles. They're galactic cannonballs, atomic nuclei accelerated to velocities so close to light speed that a single one carries the kinetic energy of a baseball pitcher in a subatomic package. What's baffling isn't just their intensity, it's how they're concentrated in a tight, unassuming patch of sky, as if the galaxy built a hidden cosmic ray gun and aimed it straight at us. Most galaxies sprinkle cosmic rays evenly across their structure, the natural byproduct of supernova shocks and stellar winds. But Centaurus A's hotspot defies this pattern, packing more punch into a single beam than the rest of the galaxy combined. The leading theory points to the supermassive black hole's monstrous jets, which might funnel particles into a narrow, high-energy beam like a cosmic lightning rod. As material spirals toward the black hole, magnetic fields could whip charged particles to ludicrous speeds, then slingshot them outward in a focused torrent. Picture a natural version of the Large Hadron Collider, but scaled up to galactic proportions and with no off switch, yet there's a glaring problem with this explanation. The hotspot isn't aligned with the black hole's known jets. Instead, it sits off-center in a region where the jets should have long since dissipated. This misalignment has spawned wilder theories like the presence of a hidden pulsar, a rapidly spinning neutron star with a magnetic field trillions of times stronger than Earth. Such an object could, in theory, accelerate particles to extreme energies, but even the most powerful pulsars struggle to match the hotspot's output, leaving astronomers scratching their heads. The real enigma lies in the particles themselves. When scientists trace their paths back to the hotspot, they find something peculiar. The beam contains an overabundance of heavy atomic nuclei like iron and silicon, compared to the usual proton-dominated cosmic rays. This suggests the accelerator isn't just powerful, it's selective, favoring certain materials over others. Some researchers speculate this could hint at the wreckage of a devoured star, its heavy elements shredded and forged into cosmic bullets by the black hole's gravity. Others wonder if we're seeing the aftermath of a dark matter annihilation event, where exotic particles collide and decay into standard matter with a heavy element bias. What makes this hotspot so revolutionary isn't just its existence, it's the questions it raises about nature's limits. If a natural process can concentrate particles to such extreme energies, what else might be lurking in the universe's corners, unseen and unimagined? And if this turns out to be something entirely new, a cosmic ray factory unlike anything in our models, then Centaurus isn't just breaking rules, it's rewriting them. At the heart of Centaurus A, something impossible is happening. The galaxy's nucleus flickers like a candle in a hurricane, its brightness swinging wildly over timescales that defy physics as we know it. Most supermassive black holes change their output gradually, their light curves smoothing out over years or decades as their gargantuan accretion disks churn like slow-moving whirlpools. But here, the core's luminosity can spike or plummet within hours, as if someone's flipping a cosmic light switch at random intervals. These aren't subtle variations either. Some fluctuations blast out double the galaxy's normal brightness in X-rays before vanishing just as quickly, leaving astronomers scrambling for explanations. The leading theory blames turbulence in the black hole's accretion disk. Normally, these disks behave like orderly cosmic faucets, with gas spiraling inward in a predictable, albeit messy, flow. But Centaurus A's disk might be caught in a state of extreme instability, its inner regions fragmenting into dense clumps that plummet toward the black hole in erratic bursts. Picture a logjam breaking apart in a river. Some chunks flow smoothly while others tumble violently, creating splashes of energy each time they hit the event horizon. These crashing gas boulders could explain the sudden flares, their collisions converting gravitational energy into intense radiation flashes. Yet there's a problem. Even the most unstable accretion disk shouldn't produce variations this rapid. The inner edge of the disk, where most light is emitted, orbits far too slowly for our scale, flickering unless the black hole is spinning at nearly the speed of light, warping spacetime so severely that it compresses these processes into shorter timescales. That would make Centaurus A's black hole one of the fastest spinning behemoths ever detected, a cosmic top teetering on the brink of physical possibility. But spin might not be the only factor. Some researchers argue we're seeing the effects of a hidden magnetic revolt. Powerful magnetic fields, twisted like rubber bands by the disk's rotation, could snap suddenly, releasing pent-up energy in explosive reconnection events, the same process that triggers solar flares but scaled up to black hole proportions. These magnetic snapshots would inject energy directly into the disk's upper layers, creating brief, intense hotspots, visible as flickers across millions of light years. The wildest possibility, these flickers might not originate from the disk at all. A small but growing faction of theorists suggests they're echoes from a second black hole lurking nearby, its gravity tugging on the primary's disk during close passes and stirring up violent turbulence. If true, Centaurus A's nucleus wouldn't just be unstable, it'd be locked in a gravitational tango with an invisible partner, their dance shaking the very fabric of spacetime. What makes these flickers so revolutionary isn't just their speed, it's what they reveal about black hole behavior at the edge of predictability. Most cosmic objects follow rhythmic patterns, their changes governed by size and rotation. Centaurus A's nucleus tosses that rulebook aside, proving that even the universe's most relentless monsters can have tantrums too erratic to forecast. And with every unexplained spike or dip, it reminds us that some cosmic clocks don't tick, they stutter. Deep within the furnace-like chaos of Centaurus A's core, where temperatures should vaporize anything for light years around, lies one of the galaxy's most baffling contradictions. A ring of icy dust particles stubbornly surviving mere parsecs from the supermassive black hole's maw. This isn't just unexpected, it's like finding a snowball sitting unscathed in a blast furnace. Thermodynamics demands this dust should have sublimated into gas eons ago, yet here it lingers, its frigid particles glowing faintly in infrared as they quietly defy the laws of physics. The puzzle begins with the dust's temperature. Measurements peg these grains at around -250 degrees Celsius colder than Pluto's surface, yet orbiting dangerously close to a black hole that routinely heats surrounding matter to millions of degrees. Normally, such extreme proximity would bake the dust into oblivion within days, leaving behind only a wisp of ionized gas. So how does this icy halo persist? One theory suggests the dust might be shielded by a cosmic labyrinth, dense, cooler gas clouds acting like thermal barricades that absorb the black hole's fury before it reaches the dust. Picture standing behind a thick brick wall during a wildfire. The inferno rages nearby, but you're spared the worst of the heat. But there's a catch. Detailed spectral analysis reveals the dust isn't just surviving, it's actively replenishing itself. The particles show chemical signatures of ice-coated silicates and hydrocarbons, materials that should disintegrate under constant X-ray bombardment. This has led to a radical idea: the dust might be reforming as quickly as it's destroyed. Some researchers propose that molecules blasted apart by radiation are recombining in the relative calm between shock waves, like a cosmic game of molecular Tetris where the pieces keep fitting back together. The most tantalizing clue comes from the dust's motion. Unlike the frenzied orbits expected so close to a black hole, these particles drift in slow, orderly patterns, almost as if they're riding gentle gravitational eddies. This bizarre calm has sparked speculation about an unseen force, perhaps delicate magnetic fields acting like cosmic refrigerators, channeling heat away while stabilizing the dust's fragile structure. Or maybe the black hole's accretion disk isn't a continuous inferno, but a patchwork of hot and cold zones, with the dust cleverly navigating between the thermal minefield. What makes this icy enigma so revolutionary isn't just its defiance of thermodynamics, it's what it reveals about the hidden complexity of black hole environments. If dust can find sanctuary in the most hostile places imaginable, then our assumptions about how matter behaves under extreme conditions might need a rewrite. And in Centaurus A's case, that rewrite could change how we see every active galaxy in the cosmos. Among the many mysteries lurking in Centaurus A, some of the most elusive aren't seen or heard, they're felt. Deep within the galaxy's core, subtle tremors ripple through the fabric of spacetime itself, gravitational waves so faint, they're more like cosmic whispers than the usual thunderous crashes we detect from black hole mergers. These aren't the confident signals picked up by observatories like LIGO and Virgo. They're fleeting, ambiguous murmurs buried in the noise, teasing us with hints that Centaurus A's supermassive black hole might be up to something extraordinary. The intrigue starts with the data. Over the past decade, gravitational wave detectors have occasionally caught strange, low-frequency hums that seem to align with Centaurus A's position in the sky. Unlike the sharp chirps produced by colliding stellar mass black holes, these signals are diffuse, lingering for weeks or months before fading away. Imagine trying to eavesdrop on a conversation through a thick wall. You might catch a word or two, but the rest is lost in muffled uncertainty. That's the challenge here. These waves hover right at the edge of detectability, leaving scientists debating whether they're real or just statistical flukes. So why would Centaurus A's black hole produce such subtle ripples? One compelling theory suggests it's not alone, that a second, smaller black hole might be orbiting it in a slow cosmic dance. As the two spiral closer over millennia, their gravitational pull would warp spacetime, emitting waves too faint for our current instruments to clearly resolve. It'd be like sensing the vibrations of a distant drumbeat while standing next to a roaring waterfall. The signal exists, but the cosmic background noise drowns it out. Another possibility is even stranger. Some researchers speculate these whispers might come from the black hole's surface, or more accurately, its event horizon. According to cutting-edge theories, turbulent plasma or magnetic instabilities near the edge could create low-frequency spacetime ripples without the need for a collision. Picture a lake disturbed not by a falling boulder, but by the steady lapping of waves against the shore, a gentler, more persistent disturbance. If true, this would mark the first indirect evidence of continuous gravitational waves from a supermassive black hole, a phenomenon predicted by theory but never confirmed. The frustration lies in the uncertainty. Unlike optical or radio observations, gravitational wave detections can't yet be pinpointed with enough precision to say definitively, yes, this came from Centaurus A. The signals overlap with noise from Earth seismic activity, even passing trucks, and the galaxy's great distance makes isolating a clean signal nearly impossible. It's like trying to hear a pin drop in a hurricane, yet the potential payoff is enormous. If these whispers are real, they could reveal secrets about black holes no other signal can. Gravitational waves carry information about their source's mass, spin, and even the shape of the spacetime around it. A confirmed detection might let us weigh Centaurus A's black hole with unprecedented accuracy or prove whether it's truly paired with a hidden companion. More tantalizingly, it could offer a glimpse into the black hole's day-to-day life, not just its cataclysmic mergers, but the quieter, ongoing processes shaping its existence. For now, these whispers remain cosmic maybes, lingering in the data like half-heard rumors. But as gravitational wave detectors grow more sensitive, and as astronomers learn to sift through the noise with sharper tools, Centaurus A's quietest secrets might finally break through, proving that sometimes the universe's most profound truths are spoken in a hush. Among the scientific mysteries of Centaurus A, one particularly wild theory has captured imaginations beyond academia: the fleeting suggestion that some of its bizarre radio signals might not be natural at all. A few years back, an unusual pattern in the galaxy's emissions sparked whispered speculation about artificial origins, with a handful of researchers openly pondering whether we might be glimpsing the footprint of an alien megastructure. The idea wasn't entirely baseless. Certain radio bursts from Centaurus appeared unnaturally regular, almost like a coded pulse, unlike the chaotic static typical of active galaxies. The most provocative signal came in 2019, when astronomers detected a sequence of microwave emissions repeating every 47 hours with eerie precision. Natural cosmic objects rarely keep such metronomic timing. Neutron stars might pulse predictably, but their rhythms are measured in milliseconds or seconds, not days. This unusually slow cadence fueled speculation about a possible technological source, like a massive energy transmitter or a Dyson swarm, a hypothetical network of solar collectors built by an advanced civilization to harness a star's power. For a brief moment, it seemed science fiction might be colliding with reality, but here's where skepticism stepped in. Further analysis revealed the signal's regularity was likely an illusion caused by an observational quirk. Because Earth's rotation limits how long telescopes can monitor a single patch of sky, gaps in data collection created a stuttering effect, making random bursts appear artificially spaced. Once researchers accounted for this, the pattern dissolved into statistical noise. Even more damning, the signal's frequency drifted over time, a telltale sign of natural plasma interactions, not engineered transmission. Yet the megastructure rumor persists, and for good reason. Centaurus A's sheer weirdness makes it a magnet for unconventional theories. Its warped dust lanes, erratic jets, and missing dark matter already defy textbook explanations, so why couldn't it harbor something even stranger? While Occam's razor favors natural causes, the galaxy's track record of breaking rules leaves room for healthy curiosity. After all, science advances by questioning the improbable, and in a universe as vast as ours, dismissing possibilities outright might be the only thing more dangerous than believing too easily. What makes this rumor so compelling isn't its plausibility, it's what it says about our relationship with the unknown. Centaurus A doesn't just challenge astrophysics, it taps into humanity's oldest instinct to look at the unexplainable and wonder, what if? And sometimes that wonder, not the answer itself, is what drives discovery forward. Hovering on the fringes of Centaurus A, far from the chaos of its core, lurk stellar anomalies that refuse to die. Cosmic revenants astronomers have nicknamed zombie stars. These aren't your typical white dwarfs or neutron stars quietly cooling into oblivion. They're stellar corpses that inexplicably flare back to life, burning with renewed vigor millions of years after their supposed deaths. Picture a candle that not only relights itself but erupts into a bonfire, defying every law of stellar evolution we thought we understood. The most chilling examples are found in the galaxy's sparse outer halo, where ancient stars should be fading into darkness. Instead, telescopes have spotted multiple objects pulsing with unexpected brightness, some glowing with the telltale blue hue of rekindled nuclear fusion, others emitting bizarre X-ray signatures reminiscent of much younger stars. One particularly notorious case, catalogued as Cs UJ 132527, appeared as a faint dot in early surveys before abruptly surging to 20 times its original luminosity in less than a decade. It's as if something reached into the star's grave and jump-started its heart. So how does a dead star reignite? The leading theory points to Centaurus A's supermassive black hole as the ultimate necromancer. Though these zombie stars orbit far from the galactic center, they might still feel the black hole's gravitational influence. If a stellar corpse drifts too close to a dense cluster or molecular cloud, perhaps one displaced by the black hole's gravitational tides, it could steal enough material to restart fusion in its core. Imagine pouring gasoline on cold ashes. Under the right conditions, even long dead embers can burst into flames. But there's a twist that complicates this neat explanation. Some of these undead stars show chemical anomalies, abnormally high amounts of carbon and oxygen in their atmospheres, that suggest they're not just stealing gas, but undergoing something far stranger. A radical alternative theory proposes these stars might be feeding on dark matter. If certain hypothetical dark matter particles accumulate in a dead star's core, their annihilations could release enough energy to reignite fusion, essentially turning the star into a dark matter-powered lantern. While speculative, this idea gains traction from the zombies' preferential appearance in regions where simulations predict dark matter density peaks. The most unsettling cases, however, are the repeat offenders, stars like Halo Object 47, which has flared and faded 3 separate times over the past century. Normal stellar rejuvenation can't explain this stop-start behavior. Once a dead star reignites, it typically burns steadily until its stolen fuel runs out. One provocative study suggests these stars might be trapped in a cosmic catch-22. Their reignition heats surrounding gas, pushing it away and cutting off their fuel supply until the gas drifts back centuries later, triggering another outburst. It's a stellar version of binge and purge, playing out on a timescale only the universe could orchestrate. What makes these zombie stars more than just celestial oddities is what they reveal about the limits of stellar physics. Every textbook states that stars follow predictable life cycles: birth, maturity, death, but Centaurus A's halo proves the universe enjoys rewriting its own rules. Whether through black hole meddling, dark matter alchemy, or forces we've yet to imagine, these resurrected giants challenge our most fundamental assumptions about how stars live, die, and occasionally refuse to stay dead. And in their flickering light, we might just find clues to phenomena far stranger than anything we've dared to hypothesize. Somewhere in the tangled heart of Centaurus A, light plays tricks with time itself. Astronomers have caught glimpses of celestial events unfolding in reverse order: flares that brighten before they erupt, outbursts that echo years after their origin, and beams of radiation that seem to linger far longer than physics should allow. These aren't glitches in observation, they're the unmistakable fingerprints of space-time warping under extreme gravity, bending light's path so severely that the universe's strict chronology starts to unravel. Take the case of X-ray flare Echo 19, a burst of energy detected in 2016. Telescopes first spotted the initial flash near the black hole's accretion disk, a typical hiccup from a feeding supermassive beast. But then, 3 years later, an identical flare appeared farther from the black hole, as if the event had somehow rewound and replayed itself at a greater distance. The explanation lies in what physicists call a light echo, where radiation from the original explosion ricochets off intervening dust clouds, taking detours through curved spacetime that stretch its journey by years. It's the cosmic equivalent of shouting into a cave and hearing your voice bounce back from unseen walls, except here, the walls are the fabric of the universe itself, and the echo arrives with enough delay to rewrite our perception of cause and effect. But the real mind-bender is how these delays vary unpredictably across Centaurus A. Near the warped dust lane, some light echoes arrive decades late, while closer to the jets, delays shrink to mere months. This inconsistency suggests the galaxy's core isn't just curved, it's crumpled, with pockets of spacetime twisted into complex knots by the black hole's rotation and the lingering gravitational scars of past mergers. Imagine tossing a handful of marbles onto a trampoline distorted by hidden weights. Each marble would roll along a different path, some speeding up, others slowing down, all tracing the unseen contours below. That's how light behaves here, its journey warped by invisible topography in ways we're only beginning to map. The most tantalizing echoes come from regions where time itself seems to stutter. In 2021, researchers tracking ultraviolet emissions near the core noticed something bizarre: a series of pulses that repeated faster than their initial detection, as if the light had been caught in a cosmic eddy where time flows backward relative to its surroundings. While technically a trick of perspective likely caused by light looping around the black hole's ergosphere before escaping, it's a visceral reminder of how thoroughly extreme gravity defies intuition. Picture a river where water upstream flows westward while downstream currents rush east. In Centaurus A's core, spacetime's currents might churn with similar contradictions, creating localized pockets where the arrow of time bends to the black hole's will. What makes these time-delayed signals more than just curiosities is their potential to reveal the black hole's hidden structure. Every warped light path carries encrypted data about the mass and spin of the object distorting it, much like how a fingerprint's ridges speak to the hand that made it. By untangling these delays, astronomers have already deduced that Centaurus A's black hole rotates at nearly 90% the speed of light, a breakneck spin that further contorts spacetime into a funhouse mirror of temporal anomalies. And with every new echo detected, we inch closer to answering the galaxy's most persistent question. In a place where light itself can't decide which way to flow, what other rules might be up for grabs? Deep within Centaurus A's swirling gases, something violent and invisible has left a cosmic crime scene, a vast region where hydrogen clouds streak outward at thousands of kilometers per second, as if blasted by a colossal, unseen projectile. Astronomers call this the bullet phenomenon, but there's no visible bullet. The gas behaves like it's been punched by an invisible fist, its trajectory too precise and energetic to be explained by ordinary forces. This isn't just random turbulence, it's evidence of something massive and dark moving through the galaxy like a ghostly wrecking ball. The most striking feature of this phenomenon is its sheer scale. The affected gas spans over 1,000 light-years, with a distinctive cone-shaped debris pattern reminiscent of a high-speed impact. Yet when scientists scan the region for the culprit, a rogue black hole, a neutron star, or even a stray galactic fragment, they find nothing. The leading theory, a dense knot of dark matter, invisible to telescopes but weighing as much as a small galaxy, may have plowed through the area like a cosmic cannonball. Unlike normal matter, dark matter doesn't interact with light or gas, so it would leave no visible trace, only gravitational aftershocks in its wake. But the dark matter explanation isn't perfect. Simulations show that even the most concentrated dark matter clumps shouldn't produce such a clean, focused shockwave. This has led to wilder possibilities, like a primordial black hole, a hypothetical relic from the early universe, tiny but impossibly dense, zipping through the gas at relativistic speeds. Others suggest the bullet might not be a single object at all, but a collapsing magnetic flux tube, a spaghetti-like strand of twisted magnetic fields that snapped under pressure, releasing pent-up energy in a single explosive recoil. The real enigma lies in the gas's motion. Instead of scattering chaotically, the displaced clouds move in eerie unison, as if guided by an unseen force. Some researchers argue this could be evidence of dark fluid, an exotic form of dark matter that exerts not just gravity, but a subtle, drag-like resistance as it moves through normal matter. Imagine stirring honey with a spoon. The honey clings to the spoon as it moves. If dark matter behaves similarly, it might have dragged the gas along with it, leaving this bizarre, coordinated pattern. Yet the most tantalizing clue comes from the bullet's aftermath. The disturbed gas region glows faintly in X-rays, suggesting the impact heated it to millions of degrees. But there's no lingering heat source, just the cooling remnants of a catastrophe without a visible cause. It's like finding a forest flattened by an explosion, with no crater or shrapnel to explain the devastation. What makes this phenomenon so unsettling isn't just the absence of a culprit, it's the reminder of how much of the universe remains hidden from our eyes. If something this powerful can move through a galaxy without leaving a visible trace, what other invisible forces might be shaping the cosmos in ways we've yet to imagine? Centaurus A's phantom bullet isn't just a mystery, it's a warning. The universe plays by rules we're only beginning to glimpse, and sometimes the most violent events leave no fingerprints at all. Centaurus A isn't just alive with chaos, it has a pulse. Deep within its core, astronomers have detected rhythmic energy surges, rising and falling with the steady cadence of a cosmic heartbeat. These aren't the erratic flares or violent outbursts we've seen elsewhere in the galaxy. They're precise, almost metronomic pulses of X-ray and radio energy, repeating every 8 hours like clockwork. For something so massive, a supermassive black hole surrounded by swirling, superheated gas, this regularity defies expectations. It's as if the galaxy's violent heart has found a way to beat in perfect time despite the turbulence surrounding it. The leading explanation points to the black hole's feeding process. Imagine a pendulum swinging back and forth, except instead of a weight, it's a clump of gas the size of a solar system, orbiting just outside the event horizon. Every 8 hours, this doomed mass reaches the innermost stable point of its orbit, where tidal forces from the black hole strip away a layer of material. That stolen gas plummets inward, releasing a burst of energy as it vanishes forever, while the surviving chunk swings back out, only to return hours later for another round of cosmic cannibalism. This cycle, stretch, tear, flare, repeat, creates the illusion of a heartbeat, a rhythmic flicker in the darkness. Yet there's a problem. For this heartbeat to remain so consistent, the black hole's accretion disk would need to be unusually smooth and stable. Most supermassive black holes devour matter in messy, unpredictable gulps, their disks riddled with clumps and spirals that disrupt any regular pattern. Centaurus A's disk, by contrast, seems to have found a strange equilibrium, as if the chaos has somehow synchronized itself. Some researchers believe magnetic fields are the hidden conductor here, their invisible lines of force orchestrating the gas into orderly streams that feed the black hole in steady increments. Others speculate the disk might be nudged into rhythm by a smaller black hole orbiting nearby, its gravitational tugs acting like a metronome for the larger beast's meals. The most fascinating clue comes from the pulses themselves. Unlike a human heartbeat, which weakens under stress, Centaurus A's grows stronger during galactic disturbances, like the passage of a gas cloud or a flare from the jets. It's as if the black hole's rhythm doesn't just persist through chaos, it thrives on it. Recent observations even suggest the heartbeat might be speeding up very slightly over time, as if the galaxy's core is gradually spinning faster, winding itself tighter like a coiled spring. What makes this phenomenon so mesmerizing isn't just its precision, it's the eerie familiarity. In a universe where randomness reigns, finding something so orderly feels almost comforting, like spotting a familiar face in a crowd of strangers. But beneath that rhythm lies a deeper truth. Even the most violent corners of the cosmos can harbor hidden patterns if only we know how to listen. And in Centaurus A's case, every pulse is a reminder that chaos and order aren't opposites, they're partners, dancing to a tune we're only beginning to hear. From warped dust lanes that defy mergers to phantom stars that refuse to die, from a black hole that flickers like a faulty light bulb to invisible bullets tearing through space, Centaurus A isn't just a galaxy. It's a cosmic rebellion, a place where the universe tosses out the rulebook and dares us to make sense of the chaos. Every one of its 30 bizarre phenomena, from the missing dark matter to the inexplicable zombie stars, forces us to confront how little we truly understand about the engines that power galaxies. Think about it, this single galaxy hosts a supermassive black hole with a heartbeat, jets that twist like disobedient fire hoses, and a halo of ultraviolet glow with no obvious source. It's missing globular clusters it should have, produces neutrinos it shouldn't lack, and hides icy dust where physics insists there should only be fire. And then there are the echoes, ghostly light from vanished explosions, replaying like cosmic voicemails delayed by centuries. Each of these isn't just a curiosity. It's a crack in the foundation of our astrophysical models, a signpost pointing toward truths we haven't yet imagined. What makes Centaurus so extraordinary isn't just the volume of its mysteries, it's how they intertwine. The same violent mergers that may have stripped its dark matter also sculpted its jagged dust lane. The black hole's tantrums power both the high-energy particle storm and the eerie symmetry of its radio lobes. Even its quietest corners whisper secrets. The faintest infrared flicker might hold clues to the missing neutrinos, and the coldest dust could explain the galaxy's improbable ultraviolet halo. This isn't a collection of oddities, it's a single, sprawling puzzle where every piece reshapes the others. So what else lurks in Centaurus A's shadows? With every answer, we uncover 10 new questions. Could those phantom supernovae hint at entirely new stellar life cycles? Might the crooked X-ray jet be tracing the shape of invisible dark matter? And if we're wrong about something as fundamental as how galaxies hold onto their gas, what other cosmic truths might need rewriting? The universe loves a good plot twist, and this galaxy is its masterpiece. If these mysteries ignite your curiosity, you're not alone. The greatest discoveries start with a single question, so hit subscribe because the next cosmic revelation could be just one observation away. Until then, keep looking up. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and Centaurus A is proof.